folks, let's talk about abbreviated electron configurations and how to use the periodic table to predict what your electron configuration will be. We're actually going to start with how to use the periodic table to write your electron configurations, because the orbital diagrams are great, but it's a lot of work to draw all those lines and arrows. So there has to be a way. And also this will help you figure out how to draw the lines and arrows, what order they go in. So there's a trick to this. When you look at the periodic table, you know that every time the atomic number increases, you're adding an extra electron. So hydrogen has one electron, helium has 2, lithium has 3, beryllium has 4. And you know that you fill your orbitals in order from low energy to high energy. So every time you add an extra electron, you are kind of going that next step in terms of your orbital filling, adding one extra electron as you go from element to element. And since you always start bottom up, you can use the periodic table to help you figure out what that electron configuration should look like. You know you can fit 2 electrons in the 1s orbital. So our first 2 electrons go into the 1s orbital. So that's hydrogen and helium. If you keep going, you start the 2s orbital next. So 2. And then lithium and beryllium, electrons 3 and 4, go into the 2s. And then once you get there, you get to the 2p's. And so the next 6 electrons, which are boron through neon, are putting electrons into the 2p orbital. Next up is your 3s, and that's going to be 2 electrons worth, sodium and magnesium. And then you get to your 3p, which will take your next 6 electrons. Have you noticed there's a pattern here? Okay, what I need you guys to understand as we get starting, and we're going to keep on going, is that the periodic table reflects not only chemical and physical properties, but actually electron configurations. They're super, super tied together. They're basically one and the same thing. So as you look at the periodic table, the first row represents filling that first shell. The second row, the second period, represents filling the second shell. The third period represents filling that third shell, so on and so forth. And so the row number that you're on represents which shell you're filling. So the first row is n equals 1, n equals 2, 3, 4, 5, 6, and 7. And that's as far as we fill with ground state electrons. And then where in the periodic table you are tells you which orbital, which letter you're filling. And if you count within that section, how many electrons you have to put into it. So this first section, over here on the left, this is what we call the S block. And helium belongs to the S block because on the first level there's only an S. So this represents your S block. These electrons, you are filling the S orbital. Let's take a look at ptable.com to see what this looks like. So as I look at hydrogen here, you see in the center of the screen the orbital diagram. Hydrogen has 1 electron in the 1s. Helium has 2. Lithium, its outermost electron is going into the 2s, and beryllium has a second one there. For potassium, our outermost electron is going to be going into the 4s, and potassium has 1 electron there, 4s1. Calcium's 2 spaces over in this S block, 1, 2, and its outermost electron configuration is 4s2. So that left-hand column, that's our S block. The right-hand side of the periodic table, this big rectangle over here, this is our P block. All of those elements have their outermost electrons going into a p orbital, and the number of the p is the row number that it's on. So if I jump back to ptable.com, I take a look at boron. It has 1 electron because it's in the first spot, filling the 2p orbital. Something like nitrogen, which is 1, 2, 3 spaces over, has 3 electrons into the 2p orbital. Sulfur, I'm on the 3rd row, so I'm filling the 3p, and it's 1, 2, 3, 4 spaces over. Iodine, I'm on the 5th row. And so I'm filling my 5 P's, and I'm 1, 2, 3, 4, 5 spaces over. So my electron configuration will have 5 electrons in the 5P. The center of the periodic table is where things get a little bit more complicated, but still not crazy. Your transition metals in the middle here, these represent filling the d orbitals. So this is called our d block. Now, you'll remember from when we did orbital diagrams that the d orbitals were a little bit out of order. We filled the 4s before we filled the 3d. So these, if it's on the 4th row, it's the 3d. If it's on the 5th row, it's the 4d. You take the number of the row that you're on and you subtract 1. So if I take a look at manganese, which is here on our periodic table, its outer electrons are in the d block. It's on the 4th row, so this is the 3d, because the d's are 1 less than the row that it's on, and it is 1, 2, 3, 4, 5 spaces over. So manganese, 1, 2, 3, 4, 5 is 3d5 for its electron configuration. The f orbitals, that's my block down here at the bottom. So let's go back to my static periodic table so I can draw here. Okay, these guys down at the bottom, these represent electrons going into the f orbitals. So this is my f block. And the f orbitals are so far out of order energetically that these are 2 less than the row that they are on. So if I have something like neodymium, which is here, this is on the 6th row. Remember, these guys like fit in here. This is on the 6th row, which makes this the 4f, and it's 1, 2, 3, 4 spots over. So neodymium's outer electron configuration is 4f4. Okay, so let's do a couple here and like start from the bottom and work all the way up, right? The entire electron configuration. You're just gonna follow along with the periodic table, and it'll make sense when you see it. So give me just a second to erase. Okay, and let's pick something not crazy large, but let's take a look, say, at chlorine right here. So you have to start from the beginning because we always start from the bottom and fill up. So the first 2 electrons that chlorine has are going to go into the 1s, and there'll be 2 of them because I filled that orbital. And then I have 2s2. And then I have, so that was these guys, I have 2p6, 3s2, and then I go 1, 2, 3, 4, 5, 3p5. I have done my complete total of 17 electrons, but I've not had to sit there and draw the diagram and count it out. I've just started at the top of the periodic table and gone like a typewriter, left to right, filling in top to bottom all the electrons and where they're going. Let's look at one more. We're going to do tons of practice with this in class because this is something that is confusing until you do it a few times and then you're like, oh yeah, I get it. So have a little bit of faith and be patient with yourself as we figure it out. Let's take a look at vanadium. Here it is, 23 electrons. Okay, starting from the top, 1s2. And then I get my 2s2. And I'm over here on to the 2p, and there's 6, 1, 2, 3, 4, 5, 6 spaces there. So 2p6, 3s2, 3p6, 4s2. Okay, I'm into the D block. Remember the D's are 1 less than the row that they're on. So while this is the 4th row, this is the 3D, and I am 1, 2, 3 spots over, 3D3 for my electron configuration. Again, we'll practice in class. So hopefully it's making sense, but flag whatever questions you have and bring them with you. Put them on the video notes form so we're on the same page. Now you probably noticed or have thought ahead, if I was doing something gigantic, you know, like bismuth with 83 electrons, that'd be a real pain in the neck because I'd have to write down, gosh, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f10, 5d, 4F14, 5D10. I actually forgot which one I was going to. Did I say bismuth? We're going to go to bismuth now. 6P3. That's an awful lot to write down. I mean, I got lost track while I was in the middle of doing that, reading it off the screen. So we want a shorthand. Abbreviations are good. Let me show you 2 electron configurations, complete electron configurations. We'll talk about how we can use these to abbreviate. If I do an electron configuration for, say, argon. Argon is here, and so we can just write its electron configuration off the periodic table as 1s2, 2s2, 2p6, 3s2, 3p6. Cool. Let's go a little bigger. Let's take this next one and let's make it manganese. And so this one is 1s2, 2s2, 2p6, 3s2, 4s2, 3d5. Can I point something out? The beginning of this much, is the same. So the beginning of manganese has the same electron configuration as the noble gas argon. And so we will use our noble gases because their electron configurations are kind of a part of elements that are larger than them. We will use noble gases to form an abbreviated electron configuration. I will simply say, hey, this looks like argon. So I will write an abbreviated electron configuration where in square brackets, I write the noble gas on the previous line. So here's manganese. The noble gas one line up, that's argon. So remember, our noble gases are here on the right. Our noble gas electron configuration, and then I'll just add the extra stuff. I'll just put this 4s2, 3d10 in. And so this was for manganese. Let's look at another one. Okay, let's take barium right down here. So this is going to be for barium. I don't want to count it all the way up. I want to look back one row and find the noble gas, the one at the end of the row, on the previous line. So one period higher. That's going to be xenon. And so I'll say, yeah, all the electron configuration that would make xenon. Let me just abbreviate that. And then I include just the last little bit. So I am on the 1, 2, 3, 4, 5, 6th period. I'm in the S block, so these electrons are going in the 6s, and barium has just 2 electrons there because it's 2 steps over. Done. Much faster, much better. We're going to do one more. Let's take technetium here. Okay, so for technetium, I again look up to the one row above, find the noble gas, which in this case will be krypton, and then just finish what's on the next row. What remains, just go left to right across this final row. So I have 5s2, because I'm 2 spots through that, and then 4d, 1, 2, 3, 4, 5. 4d5. So abbreviated noble gas configurations are amazing because they're so much faster.